This video is about flat mirrors and concave mirrors. So when we're talking about mirrors, we're now not looking at light being refracted in something, but actually reflecting off of it. So we're going to use the law of reflection. The law of reflection is pretty simple. It says that if light comes onto a flat surface, the angle that it comes in equals the angle it bounces back. And so the angle it comes in is called the angle of incidence. And this is it right here. We measure just like we do with refraction. We're going to measure the angle of incidence relative to the normal, which goes perpendicular to the surface. So this is our angle of incidence, and that's going to equal our angle of reflection. That's when the light bounces back, that will be this angle, and it's also measured relative to the normal. So we have our incident ray and our reflected ray of light, our angle of incidence, and our angle of reflection, and they're equal to each other. So here's a question. Consider the diagram to the right. Which of the angles, A, B, C, or D, is the angle of incidence? So you're looking for the angle that the light comes in relative to the normal. This is our normal here. So our angle of incidence will be B. And which angle is the angle of reflection? So we have our reflected ray, and we're looking for the angle between the reflected ray and the normal, and that will be C. So this type of reflection is what we see on a flat mirror. A flat mirror, let's say we have a mirror here and we have an object up here. We label that as O. And our eyes are here. We're going to be looking at it, and we're going to be seeing an image. The light comes down and it reflects back at the same angle, and it reflects to our eyes. What it creates is called an upright virtual image. So when we look in the mirror, it looks like all the way through the mirror we could see the object. We perceive that it's on the other side of the mirror. So a virtual image is an image that exists where the light never actually reaches. In this case, our virtual image is behind the mirror. The light never goes past through the mirror, so the light all stays on this side. So this is our virtual image. But it's where the light appears to come from. You can see how if the light reflects back, but it looks like it would come from this source. We'll be talking about diverging light a lot in this next couple of lessons. The other thing that we get on a mirror is what appears to be a left-right reversal. So when you look at yourself, what you think is on your right appears on the left, and what you think is on the left appears on the right. That left-right reversal is a property of a flat mirror. We also have, in terms of magnification, the images don't appear magnified, so their magnification is equal to 1. We're going to talk about magnification for convex and concave mirrors. That will be different. But in a regular flat mirror, things appear to be the same size as they are in reality. So some of the terms that we use when we talk about mirrors and lenses, some of the variables that we're going to use are S. S is going to be for distance. And then the subscript I means it's the distance to the image. So for this picture, the distance from the mirror to the image is S sub I. We also have S sub O. That's the distance to the object. And in this case, in a flat mirror, S sub I, the distance to the image, is equal to the distance to the object. We also have the height of the image and the height of the object. In a flat mirror, the height of the image equals the height of the object, and that's why we have a magnification of 1. This is our magnification equation. This is on your equation sheet, and it says that the magnification is equal to the height of the image over the height of the object, which is also equal to the distance to the image over the distance to the object. And we'll be using this in other mirrors to find magnifications and heights of images. All right, now we're going to look at something a little more complicated. This is a concave mirror. And any mirror that is curved inward, like this, is a concave mirror. And one way to remember it is it's like a cave. You're going into something, like a little cave. This is a concave mirror. It has some properties. They're also called, sometimes we call them converging mirrors, and it has to do with the fact that the light coming in will all converge at the same point. So some of the things we talk about with this kind of mirror, we have an optical axis, the principal axis. This goes right through the center of the curve of the mirror. So this is our main axis that we're going to refer to a lot, the principal axis. We also have a focal point. If light comes in parallel to a concave mirror, it all reflects back to the same point, and this is called the focal point. And we have the focal length. The focal length is the distance from the beginning of the mirror right here to the focal point. And we're going to use this measurement F a lot in equations for mirrors. So there's some rules for concave mirrors. There's three main rules that we follow for these kinds of mirrors. First, light that comes in parallel to the principal axis. So this is our principal axis. Any light that comes in parallel to that is going to reflect back through the focal point. So if it comes in parallel, it reflects back through the focal point. Any other point it comes in parallel, it will reflect back to the focal point. Second, light that comes through the focal point will reflect back parallel. So this is pretty much the opposite. Now we have light coming in through this focal point, hits the mirror, and it reflects back parallel. Light that comes in through the focal point hits the mirror and reflects back parallel. Our third rule says that light directed at the center of the mirror will reflect back at the same angle on the opposite side. So this is our simple law of reflection. The light that comes in reflects back at the same angle. The incident angle is equal to the reflected angle. So we're going to use ray diagrams for concave mirrors. This part of optics is where we're looking at light as a ray. This will help us see how images will appear on certain types of mirrors. So they will show light that comes off the top of this. If it hits at different points in the mirror, where will it appear? And as a result, where will the image of the object appear? So we're going to draw a few select rays, and that will help us see the images of the objects. Ray diagrams help us determine the location of the image, the size of the image, and the orientation of the image. Is the image upside down? Is it right side up? Is it larger than the object, smaller than the object? How far away from the mirror is the image? All of these we can get from a ray diagram. So we're going to use the rules for each type of mirror or lens to draw a ray diagram. So for the concave mirrors, we're going to draw rays for the three special cases and use that to figure out where the image is. So let's start with, we have a concave mirror. I've drawn its focal point. We're going to start by drawing the optical axis. That's the axis that goes through the center. The next step for a ray diagram is to represent the object, and we usually draw an upright arrow for our object. We don't draw the actual object itself, just a representation. And we're going to put it at a distance that we label SO. That is the distance of the object. So this is our object. It's at distance SO. So for this first example, we're going to look at where the object is past the focal point. What is its image going to look like? Now we're going to draw the three special rays using our rules from the tip of the arrow. That's where what we use to figure out where our image is. So our first rule says a ray parallel to the axis will reflect through the focal point. So we have a ray parallel to the axis. It reflects through the focal point. Next, an incoming ray through the focal point reflects parallel. So we have an incoming ray. We're always starting from the top of the object. Goes through the focal point, and it's going to reflect parallel. And finally, our third rule is a ray that strikes the center and reflects at an equal angle on the opposite side. So we start at the top of our object, we go through the center, and reflect at an equal angle on the opposite side. Now, this is a converging lens, so all of the light that comes in converges at some point. We're going to keep drawing the rays until they all three converge at a point. This is where our image will be. So we're going to draw our image there. And now we can figure out the distance SI, the distance of the image from the lens. And that will be our image from this concave mirror and this object. Now, this example, this is the same example. It led to an inverse image, so you could see that its point was below the optical axis. It's also a real image. A real image means that the light actually hits where the image is. So the light bounced off the mirror and it does touch the image. So we have a real image. Reflected light passes through the image locations. And you could take a piece of paper and project that image onto the paper. We have an inverse image upside down compared to the original. And in terms of magnification, this image is smaller than the original image. All right, let's look at another example. If I had the concave mirror and I put an object between the focal point and the mirror, when you draw your 3 special lines, you'll notice that none of the rays will intersect on reflection. This one goes here, this one goes here, and this one goes here. But there is an image. So we need to figure out where that image is. The way we find it is, instead of following the reflected rays, we're going to imagine those reflected rays came from behind the mirror. And we extend those rays, and that will show us that an object that's between the focal point and the mirror will create a virtual image. The only place those rays converge is on the opposite side of the mirror. So the result is a virtual image. That means no light actually hits the image. It's in darkness behind the mirror, but it appears to come from behind the mirror. So if I have an object exactly at the focal point, the rays will never cross and there will be no image, even if I extended them behind the mirror. So let's look at our rays. If we have a parallel ray through the focal point, and I can't do one from here to the focal point because that won't go through the mirror. The other way we can have a ray is through the center and back, and you'll notice that these rays don't converge. And even if I extended them behind the mirror, they're parallel, so they will never converge. So if I put an object at the focal point in a concave mirror, I will have no image. Finally, the last thing we're going to talk about is the mirror equation. This is also used in lenses, and this is on your equation sheet. It says that 1 over the distance to the image plus 1 over the distance to the object equals 1 over the focal length. And it's just a mathematical relationship that can tell you can use to figure out exactly where your image is going to be, if you know where your focal point is and where your object is. So let's do an example to end this. A 4 centimeter tall light bulb is placed a distance 45.7 centimeters from a concave mirror having a focal length of 15.2 centimeters. Determine the image distance and the image size. So to find the image distance, we're going to use the mirror equation. We're going to plug in, we have, these are our givens, our height of the object, our distance of the object, and our focal length. And we're going to plug in our distance of the image, our distance of the our focal length and our distance of the object to find the distance of the image. Simplify this and we get to the distance of the image is 22.8 centimeters. Since our focal point is 15.2 centimeters, that means our image is past the focal length. Now we're going to find the image size. We're going to use the magnification equation, which says the height of the image over the height of the object equals the distance of the image over the distance of the object. And we're just using magnitudes. We plug in the values that we know, and we can find that the height of the image is 1.99 centimeters. So this tells us, since our object was 4 centimeters, that our image is smaller than our object. So for this example, our image is real, which we know because SI is positive. We're going to talk about that in a little bit, but the distance from the image it's going to be on this side of the mirror. That tells us that the image is real. It's smaller than the original object. The image will also be inverted since the object is past the focal point. So whether it's inverted or not, we can figure out from the ray diagram. But the other parts we can find out from the equations. So here are some general rules in terms of sign conventions for the mirror equations. First, the focal point or the focal length is going to be positive for a concave mirror. When we talk about convex mirrors, it'll be different. But if f is positive, it means that we're looking at a concave mirror. The distance of the image is going to be positive if it's a real image and it's located on the object's side of the mirror. The distance of the image is going to be negative if the image is a virtual image and is located behind the mirror. And the distance of the object is always positive. For our purposes, you can sometimes have it negative, but for our purposes, we're going to have the distance of the object, it's always going to be on the positive side of the mirror.